You made a graph yesterday. You drew it. You put some kind of a indication of the trend. And what was the trend? How would you describe your graph that you just handed in? Linear. Linear and direct, right? Direct means when one variable goes up, the other variable goes up. So when the temperature gets higher, the volume gets bigger. And that makes good sense. You don't need to draw this, but you should have had some points up in this area here. You should have then extended all the way down, and hopefully you ended up with about negative 273. If you ended up with like 280 or whatever it was, that's fine. It's not a big deal, all right? And what I want to talk about now is what you did to locate absolute zero. So I do want you to write this down. The concept of absolute zero is fairly important. And these pair of lines is the same graph that you'd drawn. I just want you to make a little sketch of it. So when you get done that particular little paragraph, you can draw a couple of little axes here. And again, this is going to be volume. The unit doesn't matter. Actually, I wanted the brackets for the unit, milliliters. And then the x-axis, temperature, and temperature in degrees Celsius. And this is kind of a tricky thing for me to do on the thing, but you could probably do it. If I put down here that special temperature, negative 273, then what I'm going to plan, what I would like to do is I'd like to draw a line that cuts across like this. So I'm going to attempt to draw a line here. Hey, that's not bad. We'll take that line. Now, it turns out when scientists did this with other gases, it didn't matter what the gas was. The slope was different, but hey, that's not bad. Different slope, same intercept, pretty good. So the slope was different, but the intercept was the same. That x-intercept was the same. So I'm going to do that one more just because it's fun and I'm getting pretty good at it. Let's see if I can put a third gas on here. Oh, not bad. So that intercept was found to be negative 273. We call this absolute zero. According to the kinetic molecular theory, it's where theoretically all of the particles stop moving. We say they have 0 joules of energy. That's a J, by the way, joules of energy. We must start at a temperature of 0 where V is equal to 0 in order to have that nice relationship of if I double the temperature, I double the volume. You have to start with an absolute scale in order to do that. Let's draw one more sketch and then I'll be able to explain that a little better. So I've got another sketch that can go under this paragraph. Same as the last sketch, except I've moved the axis over, and I'm going to have this down here as being 0, but this is going to be 0 Kelvin. This is 0, and this is temperature, but now in the Kelvin scale. This, again, is volume in milliliters. Doesn't matter what the unit is. And I'm not worried about the different gases this time, but our line is going to head out in the same way, but now it's going to start here nicely at 0, 0. So let's have it kind of head out here. Hey, that's not bad. It's fairly straight. Again, it's just a sketch, all right? Now, with this particular representation of the graph, I now have that thing at 0, 0. If I wanted to come up with an equation for this, I could use, and you can put this underneath, if I want to use like y equals mx plus b, right, mx, oh my goodness, what a mess. If I want to use y equals mx plus b, now with this particular version, there is no b because we're at the origin, 0, 0. That means I can go back to my good old y equals kx, right? But in this case, it's going to be v equals some constant k times t. Now that little equation right there is only valid if I start at 0, 0. And it's only valid if I start my temperature at absolute 0. So I must have it in Kelvin. Now, you don't need to write any more on this graph, but let's say I had a T1 right here, and that particular T1 had a V1 right there. Don't need to write this down. Now the rate relationship works. If I double that, let's say I go T1, and I go out here twice as far, and I call that T2. If I double the temperature, because it's a linear direct relationship, what's going to happen to the volume? It's going to double. And if you take a look, I double that, and I get over to here. That's supposed to be a straight line. It's not bad. V2, I've doubled the volume. But that only works on the Kelvin scale. All right, Charles' law. There it is right there. You can write that down. So we have a direct relationship. It's, again, got to be constant pressure, fixed amount of gas. That means the P is constant and the N is constant. As T increases, V increases. V is proportional to T. That means, and we've written this down before, V is equal to some constant times T. And if I bring the T down to the bottom, there's the V divided by T is equal to a constant. And if I extend that, we've got V1 over T1 equals V2 over T2. And there's the relation equation. All right? Again, just to state, our V's can be milliliters, they can be liters, they can be meters cubed, etc., as long as they're the same. But now we have a restriction on T. T must be in Kelvin. They must be in Kelvin, all right? So we have to do conversions every time we do practice problems. And now we'll do a couple of practice problems. There's the same equation. Don't mind that. I've already done that. Practice problems. I like to rewrite them. I like to write them out because if I don't have Kelvin temperature, I've got to do a calculation. This one I've given it in Kelvin. V1 is 22.4 liters. T1, 273 Kelvin. V2, that's what we're looking for. T2, 298 Kelvin. V1 over T1 equals V2 over T2. I'm going fairly quickly. I'm hoping this isn't too traumatic for anybody. It's pretty straightforward stuff. V1, 22.4 liters. Oops, bad line there, but you got an idea too. 73 Kelvin. V2 is what we're looking for. T2 is 298 Kelvin. I got to move this guy over here. Multiply by 298 Kelvin. Multiply by 298 Kelvin. That's gone. That's gone. K is gone. K is gone. 298 times 22.4 divided by 273. All right, Sean. Now you can give it up. 20.52. 20.52. It looks like three significant digits. 20.5. Okay? And that's what? Liters? Liters. V2. We don't like it? Oh, that's fun. We don't like it. What happened here? You actually had yours get smaller. The temperature's getting higher, so it's got to get bigger. So you did a rearrange error. You have it smaller by that factor. Excellent. Way to speak up. What did we say it was? 24.5? 24.5. That's a good little check, right? Temperature went up. It's got to get a little bigger. And notice, again, going from, and this temperature is 0, and this is 25. Going from 0 to 25, hardly a change. Hardly a change. Now with this one, and people are starting to manipulate calculators, and that's great. I like to see that you guys just go ahead and start on the problem. With this one, right, we've got the V1, 12.4 liters, T1, 25 degrees Celsius. When I get a degree Celsius, right away, equals. Behind it, don't even think about it. I don't even need to see the fact that you're adding 273. I just want to know what that number is. What is that number? 298. 298 Kelvin is one that's pretty popular that we see quite a bit, and that's because this, remember, is standard ambient temperature, right? Remember, that's the temperature that's in the lab, that standard ambient temperature. So we use that number a fair bit. And then we're looking for a V2, and we have T2, and that is 125 degrees Celsius. And what's that? 398. It's 100 higher than the other one. Okay. So same calculation, V2 over D. Why did I start with 2? V1 over D1 equals V2 over T2. 12.4 liters, 298, V2, 398. times 398 to bring it to the other side, times 398. What do I have for V2? Yep. 16.6 liters. Okay? Let's look at this one. And I want to deal with this one because of the fact that we're looking for a temperature, right? And that's a little different than the last one. So in this case, we're looking for T2. This would be an incredibly geeky way to determine the temperature of your freezer. Instead of just using a thermometer, let's put a balloon in it. See how small it gets. Could be done. Our thermometers are based on contraction and expansion of a liquid, but you could do it with the contraction and expansion of a gas. All right? Liquids don't follow the same rules as gases, so it doesn't work as nice as using Charles' law for a liquid, like a thermometer. But you could do it. Now, here's why I want to deal with this one. V1 over T1 equals V2 over T2. Now, I must admit, we got a pretty high average in this class, and I made a big speech earlier on about old tests and all that. But you guys as a group are mathematically pretty strong. Your math is good. I've had classes where math is absolutely terrible. And I've always had to come up with a way to help those people with the weak math to come up with getting the right answer. Now, when you're looking for something that's on the bottom of the equation here, it takes a lot of rearranging. You've got to move one up here, and then you've got to move everything else to the other side, and you've got to make sure you're always crisscrossing. For the majority of you guys, you've probably already done it, and you're already solving for the answer, and that's great. But a neat little trick is when you have a number that is on the bottom of a fraction that you're looking for, take the entire equation and flip the whole thing over. There's nothing mathematically illegal about taking an entire equation and turning it on its head, all right? So if you're looking for T2, as you are in this case, then there's nothing wrong with writing your equation as T1 over V1 equals T2 over V2. There is nothing wrong with it. You've just taken the inverse of the entire equation. And that means rearranging becomes a lot easier for those of us who don't like to deal with the complex math. Because if you do it this way, what do we have? We've got 298 Kelvin there. We've got 4.55 liters, T2, and then I have 4.02 liters, and I'm going to multiply both sides by 4.02. It means I deal with this mathematically just like the other ones I've done. I'm going to multiply it by 4.02, and I'm going to get my temperature, and it's going to be in Kelvin, but that's okay. But that is easier than rearranging on the bottom. When you rearrange on the bottom, students always get the inverse of the answer because they isolate for T2, but it's still on the bottom of a fraction. It ends up wrong every time. Unless you're really good at that stuff, then great. What do we have for Kelvin temperature? Yeah, what do you got, TJ? 263, and we actually only have 3 significant digits everywhere, so we'll stop right there, Kelvin. Okay? If you did this before I even talked about flipping the equation, excellent. That's the way it should be done. It should be done straight up. If you did it by flipping the equation, I don't care, as long as we get the right answer. What is that in degrees Celsius? Just curiosity, because I don't always. Kristen, what do you got? -10 degrees Celsius. Okay? All right?